In this video, we learn how to identify valence electrons in atoms, and they are the electrons that are explicitly involved in bonding. And we show how the structure of the periodic table is not only linked to electron configurations, but more specifically to the valence shell electron configurations. So in previous videos, we saw that we could write down the electron configuration for any element on the periodic table by using the Aufbau principle or by using the periodic table itself as a guide. And we specifically determine the electron configuration of lead. Now this is the full electron configuration shown here, and we can write the condensed electron configuration by identifying the noble gas immediately preceding lead in the periodic table, which in this case is xenon, and we put the xenon symbol in square brackets followed by the rest of the electron configuration. Now these electrons here, representing the electron configurations for xenon, are called the inner or core electrons, and these electrons take no part in chemical bonding. The inner or core electrons consist of full shells and full subshells, and as such are quite stable, and therefore they're not perturbed to any great extent when atoms bond with each other. The remaining part of the electron configuration correspond to what we call the outer shell electrons. Now it turns out that subshell designations in electron configurations can be written in two different ways or using two different orders of subshell designations. The first involves writing the subshell designations in order of increasing energy, and this is the way we've represented it here at the moment. The second involves grouping the subshells within their designated shell or N value. So, for example, we see that electrons in the 1s subshell belong to the N equals 1 shell. Electrons in the 2s and 2p belong to the N equals 2 shell. In the 3s and 3p, they belong to the N equals 3 shell. And then we get to the N equals 4 shell. But we've still got electrons that are in the 3d shell here, these electrons in the 3d subshell. And it may be that we want to group all of the subshells at the N equals 3 level altogether. And similarly, we might want to group all of the subshells at the N equals 4 level together, all of the subshells at the N equals 5 level together, and the two subshells in the N equals 6 shell, we might want to group them together as well. So if we would do that, the electron configuration would look like this, where we've got all of the N equals 1 subshells grouped together, all of the N equals 2 subshells grouped together, all of the N equals 3 subshells together, all of the 4 level subshells together, 5 level subshells, and all of the N equals 6 level subshells all being grouped together. Now either way of representing these electron configurations are valid. And this is the condensed electron configuration for the first one. This is the condensed electron configuration for the second one. So this one has the subshells in order of increasing energy, and this one has the subshells with the same shell or same N value grouped together. I want to focus on this particular one because it becomes very useful for us in being able to identify valence electrons, and they are the electrons that are involved in bonding, and also useful for us to identify the electrons that are not available for bonding. So as we've already seen, these electrons here in the xenon core are called the inner shell or core electrons, and they're not available for bonding. These electrons here are the outer shell electrons. This part of the outer shell configuration, the 4F14, 5D10, we'll note that they are full subshells, and we know that full subshells are stable, and it turns out that these electrons, even though they are outer shell electrons, are not available for bonding. Electrons in full subshells are not valence electrons. Now these electrons here, these electrons actually belong to the shell with the highest N value for this particular atom. We're talking about lead, and the highest orbitals and the highest subshells that are being filled in lead correspond to the N equals 6 level. So the electrons belonging to the highest N value are valence electrons, or bonding electrons. This table here shows the condensed electron configurations for the main group elements, that is, elements that appear in the S block and P blocks of the periodic table. Now, what is evident here is that the electron configurations are not only related to the overall structure of the periodic table, but closely related to the specific position of an element within the periodic table. We can see that the periodic table is structured so that elements in the same group have the same pattern of valence shell electron configurations. So, for example, all elements in group 1 have the S1 valence electron configuration, meaning they have a total of 1 valence electron in that S subshell that is available for bonding. So we see there the valence shell configurations: 1s1, 2s1, 3s1, 4s1, etc. Now in group 2 we see a similar pattern. All of the elements in group 2 have the S2 valence electron configurations, meaning they have a total of 2 valence electrons available for bonding. The elements, if we pop over to the P block, the elements in group 13, they have 2 S electrons and a single P electron available for bonding. If we go to group 15, we see that there are 2 S electrons and 3 P electrons available for bonding. In group 16, we see that we have 2 S electrons and 4 P electrons available for bonding, total of 6 there. And if we go to group 18, the noble gases, we can see that in all cases, with the exception of helium, we've got 2 S electrons and 6 P electrons being available for bonding, or technically available for bonding, because we actually know that these electron configurations represent full shells and full subshells, and that these elements tend to resist forming chemical bonds and being involved in chemical reactions. Now, originally the periodic table was structured such that elements with the same chemical and physical properties were placed in vertical columns known as groups. But what we can now see is that the modern version of the periodic table is arranged such that outer shell valence electron configurations are arranged in vertical columns, and the similarity in chemical and physical properties is actually the result of having similar valence shell electron configuration. It's not surprising, therefore, that lithium, sodium, potassium, etc. all share the properties of being soft, lustrous, reactive metals that produce hydrogen gas when reacted with water. And this is because they all share similar electron configurations. Similarly, the noble gases are all monatomic, non-reactive gases, and the valence shell configurations of the noble gases show that they have completely filled shells and completely filled subshells, which is responsible for the stability and non-reactivity of these gases. Now remember that valence electrons are those electrons involved in bonding. And valence electrons include either all of the outer shell electrons or a subset of the outer shell electrons. So for all elements of atomic number less than 30, all of the outer shell electrons are considered valence electrons. For elements with an atomic number greater than 30, electrons that are in completely full subshells are not considered valence electrons. And so we can see, going back to this table here, all of these electrons here in the filled D subshells would not be considered as bonding electrons or as valence electrons. Now, staying with this table for just a moment, the importance and significance of the old Roman numeral naming conventions for groups becomes apparent. So, for example, all group 1A elements have 1 electron available for bonding, or they have 1 valence electron. All group 2A elements have 2 electrons available for bonding, or 2 valence electrons. All group 3A elements have 3 electrons available for bonding. All group 5A have 5 electrons available for bonding. All group 6A have 6 electrons available for bonding, and all group 8A have 8 electrons available for bonding technically. Again, the exception there, helium, and I say technically because these elements tend not to be involved in chemical reactions or chemical bonding. So by using the old convention for naming groups 1A, 2A, 3A, 4A, 5A, etc., we see that the total number of valence electrons available for bonding is equal to the Roman numeral number of that group, and this becomes important when we consider bonding theories later on.